Welcome back to Programming Fluency. This is section 10.3, Multi-File Programs. Until now, you have rebuilt every source file from scratch on every compile. For a big project, that wastes minutes on a one-line change. In this video, you will learn a faster way called separate compilation. Let's begin. So far, you have compiled multi-file programs with one command that lists every source file. That works, but it recompiles every file from scratch every time. For a project with 100 files, changing one line wastes minutes. In this video, you will learn separate compilation. You compile each file once into an object file, then link them together. Change one file, recompile just that one, and relink. This is the plan for this video. First, translation units, what the compiler actually processes. Next, separate compilation. GCC-C makes object files, and then you link them. Then what the linker does. It resolves symbols across files. After that, the static keyword. It makes helpers and state private to one file. Finally, two linker bugs, undefined reference and multiple definition. Let's start with the slow way, the one you already know. You run GCC, list every .c file, and produce the program in one command. This compiles every single .c file from scratch, every time. For a 3-file project, that is a fraction of a second, no problem. But for 100 files, or the 30,000 files in the Linux kernel, recompiling everything just because you edited one line wastes minutes, even hours. The fix is called separate compilation. You compile each file once into its own object file, and then you link the object files together. When one file changes, you recompile only that one. Before we go further, you need to know what the compiler actually works on. It does not compile a .c file directly. It compiles a translation unit. A translation unit is a .c file after the preprocessor has finished with it. Now the definition. A translation unit is a single .c file after all preprocessing. Every include is pasted in, every macro expanded, every conditional resolved. Each .c file becomes one translation unit, and the compiler processes each one completely independently of the others. This figure shows the idea. On top, main.c preprocesses into translation unit 1 with the stdio declarations, the add and multiply prototypes, and the main body. Below it, math.util.c preprocesses into translation unit 2 with the same prototypes plus the actual bodies. Each .c file becomes exactly one translation unit. And the compiler sees one at a time, never both together. When compiling main.c, it cannot see math.util.c at all. It only knows add exists because the header gave it a declaration. The connection between the two units happens later at link time. Now let's do it. The -c flag tells GCC, compile this file into an object file, but do not link. So gcc-c main.c produces main.o and gcc-c math.util.c produces math.util.o. Then, to make the final program, you link the object files together with one more command. Running it prints 7. So what is in an object file? An object file holds the machine code for one translation unit plus unresolved references. Main.o calls add, but the code for add lives over in math.util.o. The object file just notes, I need a function called add, and someone else will provide it. This is the payoff, the incremental workflow. The first time you compile everything and link. Then you edit one file, Say math.util.c now you recompile only that one file with gcc-c math.util.c and you relink. Notice that main.o is reused, untouched, because main.c did not change. So for a project with 100 files, editing one file means compiling one file, not 100. One caution. If you change a header, every file that includes it must be recompiled because the declarations they depend on may have changed. Let's make the linker's job visible. Each object file exports symbols, the names it defines, and imports symbols, the names it uses but does not define. The linker matches every import to an export. Look at the tables. Main.o imports printf and add, and it exports main. Math.util.o imports nothing and exports add and multiply. So main.o needs add, and math.util.o provides add. Connection made. Main.o also needs printf, which comes from the C standard library. Now the definition. Linking is combining object files into one executable. The linker resolves cross-file references from a call to its definition, assigns memory addresses, and pulls in library code. It runs after compilation. This is the full pipeline in one picture. On the compile side, each file is compiled independently. Main.c, which calls add but does not define it, becomes main.o, tagged in red, needs add. Math.util.c, which defines add, becomes math.util.o, tagged in green, defines add. On the link side, both object files feed into the linker. The bold green arc is the heart of the figure. It shows the linker resolving the reference, connecting main.o's undefined add straight to math.util.o's definition. The result is the finished executable, with every symbol resolved. Now let's meet a keyword that makes modules queen. Static. A normal function has external linkage. The linker can see it and any file can call it. But when you add static before a function at file scope, it gets internal linkage. It becomes visible only inside its own translation unit. Look at sort.c, the swap function is marked static. It is a helper used by the sorting functions, but it is not in the header and no other file can call it or even know it exists. This is C's version of a private helper. The public functions, like sort ascending, go in the header. The private helper, swap, stays hidden with static. There are two reasons to use static at file scope. First, encapsulation. Internal helpers are just implementation details. Making them static stops other files from depending on them. You can rename, change, or remove a static function without affecting any other file. Second, name safety. Two different files can each define a static function called helper, with no conflict, because each is private to its own file. Without static, two files defining helper would cause a linker error, multiple definition. So the guideline is simple. Make everything static unless it needs to be public. Only put in the header what other files actually need to call. This figure shows the pattern that professional C projects follow. The header, module.h, holds the public interface with type definitions, function prototypes, constants, and extern declarations. The source file, module.c, holds the implementation with static helpers, static file scope variables, and the public function bodies. The .h file is the interface. It is what other files are allowed to use. The .c file is the implementation. It is how the module actually works. And static marks the private details, invisible to anyone outside the file. So every module is a .h and .c pair. Let's cover the two classic linker bugs. First, Undefined reference. You compile main.c into main.o, then you try to link with just main.o. The linker says, undefined reference to add. Why? Because main.o calls add, but you forgot to include the object file that defines add. The linker searched everything you gave it and could not find add anywhere. The fix is to include all the object files in the link command, main.o and math.util.o, and a handy tip. The name right after undefined reference tells you exactly which function is missing. This is the second bug, and it is a beginner favorite, including a .c file instead of a .h file. Look at main.c, it says hash include calp.c that pastes the entire content of calp.c, including all the function bodies, right into main.c. Now calc's functions are defined in two translation units, once in main.o and once in calp.o. When you link them, you get multiple definition errors. The rule is you include headers, never source files. The fix is to include calp.h, which has only the declarations, and then link calp.o separately. Remember, a hash include with a .c almost always means a mistake. Let's recap. Separate compilation is the foundation of building real C programs. Each .c file becomes a translation unit, and the compiler processes each one independently. You use gcc-c to make an object file, and the linker combines the object files into an executable. The big win is the incremental workflow. Rebuild only the files that changed, then relink. Everything else is reused. The static keyword at file scope gives internal linkage, making a function or variable private to one file. That is C's encapsulation mechanism. And remember the two linker errors. Undefined reference means a definition is missing. Multiple definition means two files define the same name. Next, typing all these gcc commands by hand is tedious and easy to get wrong. In the next video, you will automate the whole build with makefiles.